Alright, so in the last video, we showed that this sort of interesting vector addition and not so interesting scalar product together um, satisfied the distribution law of the scalar product over vector addition. But in this video, what we're going to show is that still we can't call v plus times a vector space because it doesn't satisfy every single one of our vector space axioms. So if we look at this and we want to show that it's not a vector space, we need to find some rules that it fails to satisfy. Now, some of the rules do seem like shoe-ins for satisfaction. For example, because everything is based on in some modification of real number addition and multiplication, it seems like commutativity won't be an issue, and that like an additive zero or additive inverses, and that C times stuff, if C is 1, will preserve the product. None of that seems like it's going to be a problem. So here are two candidates for where the vector space axioms might fail. And the first one is associativity of the vector sum. So to recall, what associativity tells us is that if I have the sum of three different elements, then whether or not I evaluate the first sum and then that with the third, or if I evaluate the second sum and then the first sum, that shouldn't matter, right? In other words, that x1, y1 sum x2, y2 sum x3, y3, why that should be equal to x1, y1 sum x2, y2 sum x3, y3. Alright, it shouldn't matter how I choose to do this summation. So, if we want to show that this doesn't hold, what we want to do is evaluate the left-hand side, evaluate the right-hand side, and we come to the conclusion that they couldn't be the same. So, let's start with the left-hand side here. And what we get is that, let's start with our initial expression. So we have x1, y1 sum x2, y2, and then that collectively sum x3, y3. So we first want to resolve what's inside the parentheses here. And what we're going to get, according to, once again, recall the action of our vector sum, we get 4 times what you would think the sum would be, right? So we get 4x1 plus 4x2, comma, 4y1 plus 4y2, and that's going to be vector summed with x3, y3. Alright, so far so good. Now we're going to apply the sum again, but what's going to happen here is everything gets multiplied by 4 again. So when I take the second vector sum, what I'm going to end up with is 16x1 plus 16x2 plus 4x3, and then 16y1 plus 16y2 plus 4y3. Alright? Now, at this point, you may maybe start to see what the issue is going to be. But let's work it out anyway. If I start breaking out the right hand side and I say, all right, x1, y1, sum x2, y2, sum x3, y3, what's that going to be? Well, what we end up with is x1, y1 unchanged, sum, and then we evaluate the right hand parentheses first, and we end up with is 4x2 plus 4x3 for y2 plus 4y3. And now we're going to evaluate the second sum here, but in doing so, once again, everything gets multiplied by 4 again, and you end up with 4x1 plus 16x2 plus 16x3, and then comma 4y1 plus 16y2 plus 16y3. And once again, this is a problem, right? What we see here is if I compare the left hand side and the right hand side, those aren't the same, right? We have 16x1, we have 4x1, we have 4x3, 16x3, 16y1, 4y1, 4y3, 16y3. Now, you could certainly go out of your way to find specific values of x1, x2, x3, y1, y2, y3 that could make this work out, like if they're all 0 or something. But remember that this sum is supposed to hold everywhere, right? You're supposed to be able to take any any triple of vectors, and the associativity should hold. So our issue here now, in this case, is that if maybe x1, x2, x3, y1, y2, y3 were all, say, 1, just to make our lives easy, then these two things aren't the same. My left-hand side and my right-hand side aren't the same. So this fails, right? So since the left-hand side is not equal to the right-hand side, it fails vector sum associativity. Alright? Good. So that's one place where it fails. Another place where it fails is distribution of scalar product over scalar sum. So in the previous video, we showed that the scalar product or the scalar multiplication actually distributes over the vector sum, but it doesn't distribute over its own sums. So remember, if we look back at our setup here, C is just some constant, right? C is some real number. And what that means is that sums and products of things like C with themselves behave in the regular old real number sort of way. And so if allegedly you wanted this to be a vector space, what you need to show is that if I took a sum of scalars and I took its vector product, or its scalar product, sorry, over one of my vectors, that should be the same as C scalar product my vector, and then vector sum D scalar product my vector, right? So remember that this sum over here is taking place in the world of scalars, and this sum over here is taking place in the world of vectors. This is a vector, this is a vector, I vector sum, this is a scalar, this is a scalar, I scalar sum, right? So, as usual, if we want to show that this does not hold, I need to show my left-hand side and right-hand side don't agree. So let's start there. Let's take a left-hand side and talk about what that looks like. Well, the scalar product is not so interesting, right? We just distribute in as we typically would. And then if you wanted to rewrite this out a little bit, you could say, well, that's cx plus dx, cy plus dy. Nothing maybe too special going on there. Great. So let's take a look at the right-hand side instead. And so we have is, all right, we have c times xy plus d times xy. And once again, the scalar product here does not do anything too fanciful, right? Nothing surprising, no weird mishaps or anything like that. But now what's going to be kind of weird is we take the vector sum of these two vectors, and what we're going to end up with is 4cx plus 4dx, right? Because when we take vector sums, we multiply everything by 4 in this instance. And then 4cy plus 4dy. Well, once again, if I compare my left-hand side to my right-hand side, those aren't the same. My left-hand side is 1/4 what's going on the right-hand side, right? This is 4 times what's happening here. So those can't be the same for every x and y. It's in fact not the same for almost every x and y. Once again, you could fish out a specific x and y where it does hold, but these sort of rules are supposed to hold everywhere. So once again, since my right hand side is not equal to my left hand side, scalar product distribution over scalar sums fell. And in a way, this makes perfect sense, right? Scalar sums don't have anything weird happening to them, but vector sums do, right? Vector sums has this +4 or this ×4 thing going on. So when you try to turn the scalar sums into vector sums, something's bound to go wrong. And in this case, we saw that it did. All right. Thank you very much. See you in the next video.